My name is Chris. I'm from Facebook. I'm here to talk about Redex. Before I get started into the talk, I figured I'd give you guys a little bit of story about me, kind of where I'm coming from, the development world. I learned to program when I was 10. My dad brought home a computer when I was 8, and I would spend all day breaking it and then all night reading the manuals to try and figure out how to fix it before he got home the next day. And so he picked me up a copy of How to Learn C in 12 Easy Lessons when I was 10 for Christmas, and I was so happy I did a backflip. And by 12, I knew I was going to be a game programmer. That was my calling in life. It's what I was meant to do. I had all these ideas for cool little games. I was going to build some Star Wars-based, role-playing thing, and it was going to be the best video game. And video games are nothing if they're not graphics. The other thing about video game programming is that there's a lot of math involved. And as good as I am at computers and figuring out stuff, I don't really like math. What I do like, I ended up figuring out, is taking things that already exist and making them faster. And so that's why I'm here talking about Redex. Redex is an Android application and bytecode optimizer. It's similar to ProGuard, but it's not a replacement for it. And I want to make that very clear throughout this presentation, is Facebook uses both Redex and ProGuard in conjunction. So it's not kind of an either-or thing. We actually recommend that you use both. The difference is that Redex operates on the entire APK, whereas ProGuard only works on the Java bytecode. And what I mean by that is Redex is specifically an Android optimizer. ProGuard is any kind of Java for any platform. Redex only works on Android stuff. So why should you care about Redex? Why should you actually use it? Like I mentioned, it's specific to Android, so it operates on something called Dalvik bytecode, not Java bytecode. There's a difference. Redex also looks at the Android resources, which is a major component in the applications, your layouts, your dimensions, your graphics files. Redex will take account into how you're using those and what it can do with them as well. And because it's so specific to Android, we're able to do a lot of Android-specific whole program optimizations, is what we call them. It looks at more of the kind of the global, holistic goal of the application and makes that better, rather than simply operating on a method here, a class there, this little section of bytecode. With Redex, Facebook measures about a 25% reduction in cold start time and application size. Cold start time is something that I'll talk about throughout this application, or throughout this presentation. And it's basically how long does it take to get to newsfeed from the app not running at all, which is something that is critically important in a time-killing app. Yeah, we know we're a time-killing app. Operates on Dalvik bytecode. What does that really mean? Well, Art and Dalvik are not JVMs. They're similar to JVMs. They run Java code, but they're not actual Java virtual machines. The biggest fundamental difference is that Art and Dalvik are register-based versus stack-based. So when you compile the Java source code down to the intermediate representation, the actual opcodes in Java and in Dalvik are quite different. And in Java, you push three operands onto a stack, and then you call a method, and that method will pop them back off and get its parameters out. Dalvik, you assign some registers, and then you call a method. The registers, the choice of using registers in its instruction set architecture give Dalvik a much more expressive and a much larger instruction set architecture because of that. And that has several advantages. When building an interpreter, it's more complex to build an interpreter for this, but it's able to end up executing the instructions more quickly because there are fewer instructions to go through generally. So in a normal application build flow, You run javac to compile your Java files to .class files or .jar files. You run ProGuard on those jar files, and it will optimize them and make them better and faster. And then you run DX to convert the jar files into DEX files. Redex happens after the DX step. It takes DEX files in, and it spits DEX files out. And that operating directly on the DEX files with that more expressive ISA gives us a chance to do more optimizations that ProGuard can't do. If ProGuard did some of these optimizations, then DX wouldn't understand the Java bytecode because it wouldn't be valid Java bytecode anymore. And so it wouldn't be able to convert it into Dalvik bytecode. But once we have the Dalvik bytecode, we can screw with it in ways that ProGuard can't even imagine. So Redex, that's one of the biggest advantages over Redex, or over ProGuard that Redex has, is that it operates on the Dalvik bytecode directly. Redex also looks at Android resources. And specifically, I mean the ARSC file. So when you compile down your res directory and you run AAPT and it compiles, the Android documentations talk about how you don't actually get the .xml files in your layouts in the application. You can't read them and parse them just like XML because they're actually compiled into this .arsc file. And ARSC is very future-proof. It's very flexible. It's very well designed for expansion, but it's terribly inefficient for time and space. It uses a shitload, for lack of a better word, of space to represent not all that much information, and it uses a lot of time to parse that information because it's pointer lookups after pointer lookups after pointer lookups. You have to look up a table, to look up another table, to look up an index and a string thing that tells you to go over here. Chasing and loading data from an ARC file is an exercise in pointer chasing, and that's, if you're trying to load stuff fast, that's terrible. Redex will look at the ARC file, and it will compact it in ways that AAPT wouldn't be able to do without looking at source code. So, and Gradle has some of this with the new Android plugin, but Redex will go even farther. So Redex will find unused resources, and it will remove them from the resource table. And that's Gradle can do that. Gradle can and does do that right now. But what Redex does that Gradle can't do is it will fix up the resource IDs that are remaining, and then it will compact the table to begin with. So if you have 10,000 resources, but you only use 50, Gradle will strip out those other 9,500 resources, but it will leave the entries in the table. And so you'll still have this massive ARC file. Redex will then take that, and it will compact it down so you only actually have the 50 entries of data that you actually use. Similarly, Redex will go through and find duplicate values with different names. So dimensions are a really common one. Dimensions and colors and numbers. How many people use 12dp or 8dp? How many times do you use it in your application? Everywhere. And you probably end up using the same number for various different values because that's a good programming practice. But in optimization, you only want that value once. So Redex will go through and it will find all of the copies of 8dp, all of the copies of 12dp, and it will fold them down to one and then just say, everybody, okay, point to this one. And it will be, you get to refer to it in code with the different values like you want. But in the actual application compiled down, there's only one copy. Finally, Redex will do a limited amount of resource inlining. So if you refer to numbers, or directly to your dimensions in code, then the Android, at runtime, you have to go and look up the resources, chase down this value, load it off the disk, and say, okay, finally I have this number in a variable. Redex is able for certain numbers of these things to just say, oh, well, you want this number out of that file? I know what it is, so I'm just going to put that right in the bytecode and just bypass the entire loading process. Using the row value deduplication, we saved about 100 kilobytes out of the app just by 12dp. It's enormous. So that's another one of the major advantages of Redex over ProGuard and various other optimization schemes. Finally, whole program optimization is really where it gets interesting. Pardon me. Okay, so inlining and dead code elimination are fairly straightforward, and people probably are able to figure them out from just their name. Inlining is if I have a public int foo and a public boolean bar, and foo is calling bar and bar is very simple, then I can just inline what bar returns into foo, and boom, eliminate the method. Dead code elimination is similarly, if I can prove that this branch doesn't exist or will never get called, then I just don't have to call it, or I just don't even have to have the code there anymore. Most optimizers will do this. Some compilers even do this. ProGuard definitely does this. Redex will take it a little farther in that if it can prove that a class is unused, it will just strip the entire class out. But this is a fairly common optimizer thing. So I'm not going to go too much into that. Register allocation, on the other hand, is something that ProGuard can't do because, again, JVMs are stack-based virtual machines. Dalvik is a register-based virtual machine. And registers are important because in Dalvik or in ART, you have 65K virtual registers. And that basically means that any method can refer to 65,000 individual memory locations at once. However, in most of the instructions, there are only 16 encoded registers, and that means that if I'm gonna use a particular instruction, it can only use the first 16 instructions. Otherwise, I have to use another instruction to refer to one of the other 65K and move it in back and forth. So if a function uses more than these 16 registers at once, and then it needs to use a symbolic instruction, you have something called a register spill. And a register spill, well, I have an example here. So if I want to add the two, so if these are my registers, these are 16 registers, and I want to add the two yellow values together and put them somewhere in my functions. This is a Dalvik instruction for adding two integers. Add int v2 is the destination, so that will go into the green one, and then we're going to add the two yellow ones together. Simple, easy peasy. However, what if I want to add a low register and a high register? Can I just add and place it somewhere and then refer directly to the high register? I can't. This doesn't work. What we have to do first is we have to make room for the yellow one. So we have to take this red one, put it up in the high registers. Then we have to copy the high register one back down to the lower 16. Finally, we have to make room for another register. We have to clear out another one and put it up in the high registers again so that we have room for the destination. And then we can finally run our actual operation. So it turns one instruction into 4, and this is one of the simplest spills you can have. If we had to use one of those red values immediately after this, we'd have to spill it back in. It's called spilling because if you imagine registers as a cup, and you fill it up, then it just spills over. Spills cause heavy performance loss because, as you can see, it vastly adds to the instruction count. And then it also just ruins memory locality. So if you know much about CPUs, they'll try to keep all of the memory that you use very local and in the caches. And if you start accessing memory outside of that, then you have something called a cache miss, and it's very expensive. You have to go talk to main memory, which is much slower than CPU memory. And especially in the case of ART and ahead of time compilation, the 16 registers that Dalvik has correlate fairly well to the 16 registers on an ARM CPU. And so the Dex2Oat compiler will actually try to use real hardware registers for most of the instruction registers when possible. So if you spill out of those, then you get millions of times slower accesses. So Redex is able to avoid a lot of this by reorganizing the method so that it doesn't use more than 16 registers at once. And this is it's something called a register allocator, and it's pretty smart. DX has one, but Redex is, not to toot our own horn, is better. Okay, so that's register allocation. But these aren't really the whole program things that I was talking about. So let's talk about some whole program optimizations. Block deduplication and outlining. Outlining is something, it sounds pretty similar to inlining, and it is, but it's the exact opposite. So if I have, and this is more of a block deduplication example, but notice that the two blocks, the two execution blocks here are almost exactly the same. They take two buttons, they set some values, they increment something, and they call a couple methods. It's almost exactly the same instructions, opcodes, in each branch. So Redex can go through this and it will figure that out, and it will say, okay, well, I don't need to double this instruction count here. I can just have one set of these instructions and set up a little bit ahead of time. And the net result of this is that I don't have the opcodes, or are too long to show here, but this method will take about twice the amount of space as this method will. And so by reducing the instruction count in half, even though we're actually not executing the instructions we're removing, so it's not much in terms of speed there, but that method weighs less on disk and weighs less to load into memory. Similarly, Redex will outline methods if it can. So if you have 1,000 different things that just return some value on a subclass, then Redex can figure that out, and we'll find these methods and we'll say, okay, well, there's 1,000 different copies of this exact same method. Let's just have one method and have everybody call that one. This is the opposite of inlining, so we call it outlining, and it does a great deal. It's the opposite trade-off. So normally you inline something so that you don't have a method dispatch, but you're eating some extra code space. It turns out that Android devices are very constrained in their performance on space, and so Redex will occasionally say, okay, I'm going to eat the dispatch in order to reduce the size here. So that's deduplication and outlining. Dex file layout is probably it's the most compelling example I have here. And so I mentioned earlier that inlining and outlining are really kind of trading off size versus speed. You either have a method dispatch or you have larger instruction count. It turns out that on Android devices, size is speed. Most Android devices have pretty fast processors, but really slow, we call it disk. And this is something that's critical. Everyone in here has a really modern computer. It has an SSD. SSDs are blazing fast solid-state storage. Well, so do phones, right? No. Phones' disks are flash memory, and it's especially cheap flash memory is extraordinarily slow. It's actually, in some cases, slower than a spinning spindle hard disk. And so if you have a lot of data to load off disk, that's what you're going to end up blocking on. Our low-end devices in India, in China, in Brazil, in emerging markets, they're data constrained. They're not actually constrained in their performance on how much they can execute. They're constrained on how much they can read off the disk. They have fast CPUs, they have really small RAMs, and they have really slow flash drives. So if you load a lot of code, like Facebook does, Facebook is enormous. We have something like 150 megabytes of code to load off disk if in the entire application. You begin thrashing the working set. You begin thrashing the entire operation, or the OS memory. And it ends up being just like swap. Android devices don't have swap, but it acts a lot like it because it's the same page cache mechanisms. Okay, and so in order to show some examples about this, we're going to take a slight detour into virtual memory and how page caches work. And if you are a kernel developer, please don't come up here and punch me in the face, because this is going to be completely butchered, but we're zipping right through to one point. So imagine that this is all of the virtual memory in an application. This is all the memory we can allocate and address. And I want to grab some memory, and this is the address. It's that little dot right there, 7AF50D30. And this is and that's in my application. Well, it turns out that you can actually have another process on the device at the exact same time, which also has a reference to that exact same address, but has different data in it. How does that work? The reason it works is that you don't actually have the real address to that memory. You have a virtual address, and the kernel maps it to physical RAM. There's a bunch of magic going on, and it is indeed way more complicated than this. And again, please don't punch me in the face for saying all this. But the takeaway from this is that virtual memory is not real memory. It's managed by the kernel. And so one of the neat things it allows you to do is that you can do something called memory mapping a file. So we have here libc, which is basically the lowest level runtime on a Linux device. And we need to use a bunch of information in it. We need to run its functions. We need to get some data out of it. One of the fastest ways, the easiest way to get that stuff is you do something called memory mapping a file. And that basically just takes the entire file and it gives you an address in memory and says, this address in memory is offset 0 in this file. And then you can access that file just as if it were already in memory. And again, it's magic. And so if I want to access this red block, then I say, hey, I'm just going to go to this address. The kernel will do a bunch of stuff, and I will get that address back. One of the things that the kernel does is it will indeed read that block off disk and bring it into memory, but it will also read a bunch more of that file and bring that into memory as well, because it assumes that if I need that red block, I'm probably going to need at least something in those gray blocks as well. That's called read ahead. And it's basically a prediction that most data access is linear. And so if I'm going to use one thing, I'm probably going to use some stuff after it. And lo and behold, if I read up some more red blocks, then it will indeed just read ahead a little bit further and it tries to stay ahead of me. Okay, so now we have actually a lot more little green and gray blocks. This is a memory mapping of all of Facebook for Android's DeX files during a startup application on a fairly typical high-end phone. So the green blocks are pages in the DeX files that have not been touched yet. You'll see them turn red and gray. Red means we've actually requested that page and we're using data in it. Gray means that the kernel has read ahead or paged in the stuff preemptively, waiting for us to use it. These videos are, again, it's a video of our data accesses during the cold start of the application, and they're slowed down to about 1/4 speed. So let's see what happens. So this is what our actual cold start looks like. You can see we fill in all the red pages, we've read all this stuff, and there's various prefetching going on. And this is on a high-end phone. This one took, I think, around 4 or 5 seconds to execute in real time. Okay, this is the exact same cold start sequence on a low-end phone, around a 2011, 2012 model. As you can see, it starts, things turn gray and red, and then they turn back to green. What's happening is that this device has low memory. It has only about 1 gig of memory. And so the kernel starts reading things in, and then it needs to read more in, and then it says, oh crap, I don't have any more room. I have to evict pages out of memory. And what happens is that it ends up having to read things twice. You'll see if you look closely, there are a bunch of gray dots, and they'll go back to green, and then eventually they'll go back to red and gray again. So the kernel is doing, the kernel is reading the disk multiple times during this cold start startup. And it's still going. This particular startup on this device took 22 seconds. 22 seconds on a low-end device for a time-killing app. I don't have that kind of patience. It's still going. So the takeaway here is that locality is of critical importance. And if you can, so what it's doing when it's reading these things is it's literally reading the bytecode off disk in order to execute it and get these classes into memory. So the class order obviously really matters. If we could order it correctly, then we would prevent all these duplicate reads. We wouldn't have to read it twice, 3 times, 10 times in order to get to completion. And it's a little funny because as programmers, we think about similar methods, close methods as, what's in my package? What are the main classes that my class uses? Well, that's not necessarily what actually happens during execution. I might have this big foobar class that talks to my bangle over here, but if the first thing it runs is it goes and does this one call on this thing over here, that's actually what's important, and that's what's close during the startup. So what Redex is able to do is that. Here we go. This is the exact same device. No, this is the slow one. Sorry. So this is the exact same low-end device, but with Redex run on it with an ordered class file. Two seconds. We went from 22-second startup to a 2-second startup just by ordering the classes correctly in the Dex files. Okay, so enough about how cool we are. How do we actually use it? Redex has been really hard. It's actually been open source for a long time, but we've noticed that nobody really uses it because we didn't do any effort to make it easy to use at all. So, and especially Facebook builds with Buck, most of the world, frankly, doesn't. Everybody uses Gradle. So how do we actually get Redex into Gradle is the hard part. So you have here, this is an example of one of our ad sample apps. And it's a Gradle file. You know, I'm sure you guys, frankly, recognize this better than I do. But here's how we add Redex to it. It's pretty simple, actually, now. You add a dependency on Tim Mutton's Redex plugin, and then you just say apply plugin Redex. And poof, off you go. You get a couple new tasks. Instead of assemble debug and assemble release, you're going to want to run Redex debug and Redex release. We didn't replace, I shouldn't say we, Tim didn't replace these assemble and assemble debug and release because Redex can actually change the behavior of your app. And so we don't want to necessarily break every workflow. We want you to actually opt into it. But just run Redex debug, Redex release, and test as normally, and then poof, you will get a normally built APK that just gets given to the Redex binary, and then Redex will spit out a better APK. It has a various configuration block. You don't actually need to do any of this, but I'll go through them real quick. The version equals latest. This plugin will basically just download the Redex binary off the GitHub releases page. So unless you want a specific version, just leave it at latest, and it will download always the latest. The config file is, you can specify a .config file that has, it's basically just a JSON object, and it'll tell you kind of, it tells Redex what passes to run. If you don't have that, then you can also specify the passes as an array here, or it will just run the default ones if you leave this blank. Redex will talk to ProGuard. If you tell it where your ProGuard configurations are, that will greatly help Redex out. Like I said earlier, Facebook uses both Redex and ProGuard, and we set up all of our keep rules and stuff in ProGuard, and then Redex will obey them. And then jar files, if you have any wonky jar files, it needs to know about them, and other arguments, really just go read the help if you want other arguments. But none of these options are required. You can just leave this block out entirely, and it'll do its thing with its default settings, which are usually pretty safe and good. So again, the config file is just a JSON file. I won't go over the actual format itself, but it's fairly easy to read. You can specify the list of passes, and then for each pass, some various options if there are any for it. I do want to call out that Redex has a ton of different optimizations. Many of them only make sense in conjunction with other optimizations or with a specialized build process. So don't just add optimizations willy-nilly, be like, oh, this one sounds cool and that one sounds neat. I want to get all these together. You will likely end up with something that isn't what you expect. I don't want to say it won't work. I don't want to say it will. It's the default configuration is pretty conservative, but it will still result in a much improved APK. If you guys really want to get wild, then start trying it out. But it would probably be good to read the code because many of them do work specifically in conjunction with other things or make assumptions on how the application is written that you might not hold to. So that's most of it. I don't have time to go through many of the optimizations themselves. Like I said, there are 100 or so, and it will try to run the best ones. I do want to talk briefly about the interdex pass, which is what I showed you with the videos. That's how Redex does its class ordering. The high level thing of how to do that for your application is you collect an hprof of whatever pattern you want Redex to optimize. So for us, we collect cold start traces. So we hit the app, wait 5 seconds, take a dump. The hprof memory dump it has some class ordering information in it. Basically, we can look at the list of classes that are loaded, and then it will look at the order in which they were loaded, and then this dump classes from hprof Python script will actually produce an ordering file that Redex can use and put into your next build. You will have to add the innerdex pass to your configuration file. It is not set up in the default one because you do need this class ordering file. Once you have it, add the innerdex pass, add the cold start classes configuration option and point it to the actual classes.txt file that this Python script spits out, and then run it again, and poof, off you go. Like I said earlier, Redex is an open source project. Pull requests are very welcome. We do quarterly releases internally, but I'm told we'll actually be trying to do every other weekly Redexes to the open source world, which is pretty cool. The Gradle plugin itself is not a Facebook project, it's an independent project, and you are also encouraged to submit to that, but we're not necessarily under control of it. So just a slight disclaimer. Questions?